Oh yeah. First, what are we going to learn today? I will tell you. First, we're going to learn about Doppler radar, and then we're going to learn about redshift, blueshift, and which is another application of the Doppler effect. Then we're going to learn about what happens when waves collide. What happens when two waves hit each other when they occupy the same space at the same time? And when we answer that question, we'll learn about the principle of superposition and constructive and destructive interference. So first, the Doppler radar. Okay, back in the 1940s, we went to war with a country that was controlled by Nazis. Back then, we used to think Nazis were really, really bad people, but now we have a president who says Nazis are very fine people. So I guess we've changed our opinion of Nazis. That's okay. But back then, we felt it was in our best interest to defeat them. And so the British invented something called a radar. And here's how radar worked, okay? You had yourself on a pole, you had this parabolic dish, and this parabolic dish would put out a wave. And then it put out waves and timed them, and when the waves bounced off of something and came back, they would time how long it took for that thing to come back. And then what are they finding again? If you're going to put out a wave and time how long it takes to bounce off something and come back, what are you measuring?
The distance.
Yeah, the distance, okay? And so what they did was this thing would rotate round and round, and then you'd have some British officer sitting at a table at a console, and in front of him would be this circular screen. And this line here would go around 360 degrees, just round and around and around, and it would go round and around and around at the same time that that guy was going round and round and round. And if he detected a plane over there somewhere, then you'd see the plane, boop. And then the next time it went around, boop. And the next time it went around, boop. And you could tell where the plane was headed and how fast it was going, but you'd have to make a bunch of measurements, okay? That's original radar. Well, then people got this idea, wait, we've got this situation where if waves of a certain wavelength hit something that's in motion, okay, and these return waves have a different wavelength, then we can tell whether the person is coming toward us or away from us, and we can even actually tell how fast the person is going. So thus came about Doppler radar, where they say, hey, we're not only going to be like the old English radar that was able to defeat those very fine people, who murdered 6 million Jews, but we can also use the Doppler effect to see how fast the planes are coming towards us, and we don't have to make these measurements anymore. You see what I mean? And so with Doppler radar, that's what they do. So now if you've got some weather condition, like a bunch of clouds with water or ice in them, and you send your Doppler radar out, not only does it tell you how far away this weather system is, but it tells you how fast the weather system is coming towards you, And thus you can say, oh, we're going to have rain tomorrow. How do you know we're going to have rain tomorrow? Because we know how fast those clouds are coming toward us using our Doppler radar. You guys okay with that? That's it, that's Doppler radar. Has anyone ever seen the movie Alien?
Yeah.
The first movie? Do you remember when they're searching for where the people might be or where the alien might be? Do you remember they were looking at this device? And the device was this?
Yeah.
So you had these people who were able to play, they had the technology to travel to different planets, but their radar technology was 1940s era British radar. I thought that was pretty funny. I mean, come on, it should have been just a digital screen or something. I mean, they had to use something more than British radar. Oh my God, the monster's getting closer. How do you know? Well, because look, the monster's coming toward us, And it's like, come on, you gotta have something better than that. You can. Okay, well anyway, that's Doppler radar. Next comes redshift, blueshift. Redshift, blueshift, blackfish, bluefish. So we've got our sun, the sun. It gives us all our warmth. The sun makes us happy. The sun is beautiful. The sun is made of hydrogen. And those hydrogens are combusting. Those hydrogens are slamming together to make helium and releasing a ton of energy, right? That's how the sun works. And so you've got all these hydrogen molecules receiving energy. And those of you who have had AP chemistry can tell me, when a hydrogen atom receives energy, what happens to the electrons? Or electron? Yeah, they get excited, just like I am talking about it. Right, they get excited. And tell me, what is the lowest state that the electron occupies?
Ground state.
Yeah, the ground state. So it goes from the ground state to an excited state. And it does that when it receives energy, but not just any old energy. It has to receive a very specific amount of energy. And then it will rise to a specific energy level. Well, you guys tell me, what happens when that electron falls back to a lower energy level? Say again? Yeah, it releases energy. It gives off photons. But again, it gives off photons of very specific frequencies. Whatever the energy was required to make that electron go to the higher energy state, so it's farther away from the nucleus as it orbits the nucleus, when that electron falls to a lower energy state, it's going to give off a photon of that specific frequency, and none other but those specific frequencies. So you look at a spectrum of all of these frequencies given off by hydrogen as the electrons fall to lower energy levels, and tell me, what special type of spectrum do we call that? Say that again, Noel?
An emission spectrum.
Yeah, that's an emission spectrum. I'm just accessing all the people who have AP chemistry. So here we go. This is low frequency, and this is high frequency. And so we look at the sun's light, and the sun's light is white and beautiful because we love the sun. And then we put the sun's light through a prism, and we separate the light into the different colors. That's called dispersion of light. And the sun has all the colors of the rainbow because it is white. But the thing is, those colors of the rainbow only occupy very specific frequencies. Only those frequencies that you get when those electrons go to lower energy levels. So let's say, and now I'm going to have to pretend, because I don't have the Balmer series and the Lyman series and all those series memorized, so I'm just going to pretend. Let's say the sun, our beautiful sun, here, let me put it right here, our sun. Let's say our sun happens to be giving off these particular frequencies. It's giving off a couple of red frequencies. It's giving off an orange frequency right there. It's giving off a green frequency right here. It's, let's say it's giving off a couple of blues, maybe that guy and that guy. And then finally it's giving off a frequency in the purple range. Now that's not real, I'm just making this up, but let's just suppose the sun gives off those specific frequencies of light determined by the hydrogen atom doing its thing. So then we look at a nearby star, maybe a star that's only like 10 light years away or something, and we look at the spectrum of the nearby star. Of course, a nearby star is made of the same stuff as our sun, hydrogen, hydrogen, right? So we would expect the nearby star to have an identical emission spectrum. And it does, except for one thing. We expect to find these two red frequencies there, but the two red frequencies happen to actually be there and there. And we expect to see the orange there, but the orange is actually there. And so on. We expect to see the green there, but the green is there. We expect to see the blues there and there, but they're actually here and here. And the purple, as you can imagine, is here. All of these frequencies have been shifted. In which direction have they been shifted? To the left, to the red part of the spectrum. So you know what special type of shift we call this? Yeah, this is a red shift. All of these frequencies have been shifted in the red direction. This is a red shift. So you tell me, what does that tell me about this nearby star?
Closer.
What's that?
Closer?
It's closer than what?
than our sun.
Well, no. No, it doesn't say that this nearby star, which is 10 million, 10 light years away, is closer to us than our sun. No, that's not true. What is that telling me? All of these frequencies that I know the sun is giving off occupies these frequencies, but all of these frequencies have been shifted in the red direction. What does that tell me about this star?
Is it giving off less energy?
What's that?
Is it giving off less energy?
No. Please think about Doppler effect. This is an application of the Doppler effect after all. What does that tell me about this star? Oh my God, I'm going to hold my breath until I turn blue. Someone tell me. All the frequencies are lower than we expect. The frequencies we're perceiving are lower frequencies than the frequencies that that star is actually putting out. What does that tell me about that star? Oh my God. Yes, Alejandro.
Is the star moving away?
What were you going to say, Logan?
I was going to say it's farther.
Okay. Yeah, not farther away per se, but it's moving away from us. This is no different than the train moving away from us, where the sound of their whistle is lower than what it actually is. Right? This is the same thing. You guys okay with that? That's redshift. The sun is moving away from us. This star is moving away from us. Okay? You guys okay with that? So now we look at a star that's far away. Maybe a star that's 1,000,000 light years away. And we look at that star's redshift. Here, let me just say far away star. And we look at its redshift. And again, it's burning hydrogen. So we know our redshift, we know our spectrum is going to look like this, red, red, orange, green, blah, blah, blah. But we look at this faraway star, and its little guys are looking like this. And I'm doing this picture so you just have a visual sense of what I'm getting at. Tell me, what can I conclude about this star? Please note, you got even more of a red shift.
It's moving even faster away from us.
Thank you very much. Thank you, Gavin. I might have been here all day. Yeah, you guys okay that the star is moving faster away from us? It's moving away from us because there's a red shift, but it's moving faster away from us because his red shift is bigger than that guy's red shift. You guys okay with that? So this star is moving faster away from us. Okay, so now we got this great tool, this redshift thing. We decide we're going to look at all the stars. We're going to look at all the stars that we can see, all the stars in the universe that we can see. And we discovered something really interesting. Here's the Earth. You got some nearby stars. You got some medium faraway stars. You got some super faraway stars. And we discover that the nearby stars are moving away from us, but the medium faraway stars are moving faster away from us. And the really, really far away stars are moving even faster away from us. In fact, if you look far enough away, there's stars moving away from us at speeds that are relativistic. They're moving away from us at speeds that are starting to be close to the speed of light. They're moving that fast. So my question to you now is this. What does this tell us about the origins of the universe? How did the universe begin? Someone please tell me. Someone besides Gavin or Alejandro. Ravi, what do you say? I know you know the answer, Ravi. Tell me, how did the universe begin?
I'm guessing all came together and then.
Okay. Someone else tell me. How do you're right, but I want to hear from someone else. How did the universe begin? Yes, Maxwell?
Big Bang Theory?
Thank you. Big Bang, right? Let's say I've got myself a bomb. Okay? There's my bomb. And the bomb is going to explode. Boom. And it explodes into a bunch of pieces. Okay? And I take a photo right after the explosion. So the bomb has gone boom, and all of these pieces are moving away from the bomb. Tell me, which pieces are moving faster? If I took this photo, you know, a quarter of a second or a tenth of a second after the explosion, which of these pieces is moving faster? Please raise your hand so I know to call you, Cole.
The one furthest away from the bomb?
Thank you. The one's furthest away. How did you know?
Well, I used the same logic applied to the star race as with the bomb.
Okay. But you know what? If I took a photo a tenth of a second after the explosion, how do I know that this guy had to have been moving faster than this guy?
Well, because they blew up at the same time, and that one's already further than the rest of them, then it must be really fast.
Thank you. That's exactly right. He's farther away than this guy, and the same amount of time has elapsed, so he had to have been going faster than this guy. So do you see that this can be an argument for the Big Bang Theory, right? The fact that everything's moving away from us, and the farther away you look, the faster it's moving. Now, not everything we look at is moving away from us. How many people are aware that there's a galaxy that's going to collide with us?
Yeah.
Okay, well, what's the name of that galaxy?
Andromeda.
Yeah, so okay, so not everything, right? Andromeda is going to collide with us really, really soon, like a billion years, I think, or something. So that's something for us to look forward to. Great. But for the most part, the farther away we look, the faster they're moving away from us. And that would argue in favor of all of life starting in one place and then exploding like a bomb. Let me ask you another question. Where's the center of the universe?
Everywhere.
I don't think so. I think it's right there, the Earth, don't you think? I mean, look, everything's moving away. Like there's the bomb, all of the shrapnel is moving away, right? Doesn't that make the Earth the center of the universe? In fact, I'll be more specific. You know where the center of the universe is? The center of the universe? Right here, this space that I'm occupying is the center of the universe.
Okay.
And I try to convince my wife of that. You know. She doesn't really believe it. I really explained it well too, honey. That's me right there. I'm the center of the universe, so make me dinner. Okay, great. But okay, so you could argue, hey, Earth's the center of the universe because everything's moving away from the Earth. But Cheyenne, you say it's everywhere. Why would you say that?
I don't want to explain it in words, but like, because no matter where you are, it's like the same, it's like far away. I can't explain it in words for a second.
Okay. Hey, let's say someone living here said, I'm the center of the universe. Could he argue that he's the center of the universe? How? How would he be able to do that?
Everything's moving away.
Yeah, everything's moving away from. What's the Earth doing relative to him?
Moving away.
Yeah, relative to him, the Earth is just another one of these guys, right? Everything's moving away from him, and the farther you look, the faster it's moving, right? So he's the center of the universe, or him, or him, or him. In fact, as you said, everywhere is the center of the universe. We are all the center of the universe. We are all equally important. We're all deserving of love and consideration. And it's a beautiful thing. You guys okay with that? Hey, let me ask you one more question. What if I'm looking at a star, and he's got a redshift because he's really far away from me, but I notice that his redshift is oscillating periodically. That is, every 30 days the redshift gets less, and then every 30 days the redshift gets bigger. So I'm watching this redshift, oscillate between being a big redshift and less of a redshift. What would that tell me about this star that I'm looking at? What's that?
It's like it's rotating, it's orbiting something.
Thank you. It's orbiting something. That's our big proof. Remember that Doppler ball I had? Where when it was coming towards you it was higher pitched and when it was moving away from you it was lower pitched, that ball that made the sound? Well, that's all this star is. The star is just going around something, and half the time it's going towards you and half the time it's moving away from you. And so you get to say, oh, it must be orbiting a black hole or something if the redshift is changing. Okay, hey, that's all I got with redshift, blue shift. Does anyone have anything to add? No? Okay, then let's keep going. It is time to do principle of superposition. At the very, very beginning, in the first 10 to the negative 40 seconds, where was the center of the universe? Was that?
Where did the explosion happen?
Thank you, wherever it happened. And there is no other place, right? If our whole universe consisted of this point, you know, we can't say point in space because I don't know what you have without space. My brain's not big enough. So if that's the center of the universe, then it explodes. We're all the center of the universe, right? That's why, have you ever heard about, what is it called, background radiation? Have you ever heard of that stuff? And that's everywhere. Background radiation isn't coming from any particular place, because that background radiation is the radiation you have as a result of this big explosion. But the big explosion happened everywhere. You know, we're as we get bigger, we're still that point. So that's why the background radiation is literally just background radiation. It started at the center of the universe. Back when the universe was that one little point. It's everywhere. It comes from everywhere. Alrighty, it is time to add waves. When waves collide, when waves collide, what happens when waves collide? Would someone like to be my spring Betty? Come on, wait, no, you always get to do it. Yeah, Anise, come on up. Paul always gets to do it. Take this in, yay. Okay, and move, move, let me make sure that this wire, you don't trip over it. Okay, cool. And take a couple more steps back, just so we have more. Okay, so here's our little spring, alrighty. And I can send a pulse to Anais, there's the pulse. But the question is, what if I send a pulse to her and she sends a pulse to me? What happens when our two pulses collide with each other? Do they bounce off each other or do they pass through each other? Let me first ask you guys before I go any further, how many people say that my pulse and her pulse are going to bounce off each other? Okay, cool. How many people say they'll just pass through each other? Like two ships passing in the night. Okay, well, hey, let's find out. You ready? And yeah, you'll pluck down, and I'll pluck down, and we'll go 1, 2, 3, pluck. Okay, you ready? 1, 2, 3, pluck. Okay. Well, I don't think that got us anywhere. Here, let's try it again. 1, 2.
Stop putting it higher. I'm
Oh, I'm
trying
sorry.
to like.
Oh, that's right, the little short girl. Okay, 1, 2, 3, pluck. Good. So what do you think? Are they bouncing off each other or passing through? Well, let's try something else. Tell me, what could she and I be doing to our pulses to make it a little bit more obvious as to whether they're bouncing off or passing through? What's that?
Use the same point when you're plugging it down.
Okay, make identical pulses. Is that going to tell me whether they're bouncing off each other or passing through? What should we do with our pulses?
Do a lot of them.
What's that?
Do a lot of them.
Do a lot of them? That's going to be pretty confusing. And I hate to say no to you, but yeah, we do a lot of them, we'll get standing waves. Yeah, Sean?
Can you just make different pulses so that
Yeah.
you can see the difference?
Yeah, let's make different pulses. She'll make a big pulse and I'll make a little teeny tiny pulse. If they bounce off each other, my tiny pulse will hit her big pulse and come back to me. But if they pass through each other, then my tiny pulse makes it all the way to her, and her big pulse makes it all the way to me. You see how that works? So let's go ahead and find out. You ready? You're going to make a big pulse. I'm going to make a tiny pulse. And make your pulse super big. 1, 2, 3, pulse. So what do you think? Did her pulse bounce off of mine, or did it make it all the way to me? Let's try it again. Okay, just a second. Okay. 1, 2, 3, pulse. Here, let's do it one more time, because you're doing a good job. 1, 2, 3, pulse. What do you think? How many people say it's ours are passing through each other? Okay, good. I'm hoping so, because it looks that way to me. Her big pulse is definitely making it to me. My little pulse is making it to her. Okay? So are you okay that waves, when they hit each other, they just pass through each other? Okay? So the next question to ask is, what happens when these two waves are occupying the very same space at the very same time? And to show you that, thank you very much, Anise. Give Anise a hand. I need to show you, I took a slow motion picture, a slow motion movie of this last year. Here's what's going to happen. A student is going to send a pulse to me, and the student is plucking down, which means he plucks down so that the leading edge of the pulse is downward. But when you pluck down, it makes the trailing edge go up. So my student is giving a pulse like this, and I'm doing the same. So my pulse and his pulse are going to get together. They're going to combine. And I want you to see what happens when these two parts, the leading edges of the pulse, see what happens when they overlap each other. And then a moment later, these two guys are going to overlap. And I just want you to see what happens when they combine.
Just hit publish.
Oh, hit publish?
Yeah.
Okay. Publish. Okay, I'm gonna go. This isn't a very good picture, but it's good enough. Here it comes. Now the reflection, do you see how you get the upward pulse and then the downward pulse? And then it just goes crazy. So I want you to see that our initial pulse, my downward is leading and his downward is leading. But when those pulses reflect off of us, they get inverted. And so the next time around, the pulses actually look like this. And I think it's even clearer when those pulses combine, how these two upward pulses combine to make one big upward pulse. Let me show you that again and have you see that the pulses are actually just combining with each other.
Not hungry anymore. Should I eat the rest? Okay.
Here we go. And now watch, the first is up, and then down. And then the pulses go on the merry way, down and then up. And then here's the next one, up and then down. And then peace. Well, I'm doing this in the hopes of convincing you that when waves collide, their amplitudes add. That's all. If this wave gets with this wave, they get together, you just get the sum of the two waves. That's it. Their amplitudes add. And that's the principle of superposition, which is what we're going to learn now. Or I'm going to write on the board. When wave collides, you get the principle of superposition. And it just says this: when two waves occupy the same space at the same time, their amplitudes add. When when two waves occupy same space at the same time, their amplitudes add. I'm going to show you one example, then I'm going to have you guys do two examples on your own. Suppose I have two pulses moving towards each other. This pulse is moving in this direction at 1 centimeter a second. This pulse is moving in that direction at 1 centimeter a second. And each one of these little spaces is 1 centimeter. Okay? And I want to see what happens to those pulses over the next 2 seconds. Remember, this pulse is moving at 1 centimeter a second. This pulse is also moving 1 centimeter a second. This is going to make great demands on your ability to think spatially. This pulse, I'm going to call him the purple pulse. This pulse will be the green pulse. Okay? The next moment, the next second rather, 1 second later, someone describe for me what's going to be true about these two pulses. Yes, Sean?
They're gonna collide.
Good. They're going to collide. Tell me more. What's going to be true about these pulses 1 second later? I mean, 1 second after what you're looking at. Oh my goodness. Where's this purple pulse going to be 1 second later?
1 block to
Yeah, 1 block over. Where's this green pulse going to be 1 second later?
block to the left.
1 block over, right? Good. So tell me, if the amplitude of these pulses is 1 centimeter, right? If the amplitude of these pulses is 1 centimeter, what's the amplitude of the combined pulses going to be 1 second after this? You guys getting 2? Okay, hope so. Hope so. Because if you're not getting it, then there's nothing I can do for you. I'm hoping that you see that this purple pulse is going to be right there 1 second later, but so is the green pulse. And so they both have an amplitude of 1. So your total pulse is going to have an amplitude of 2. You're going to have something that looks like this. So I've got a single pulse with an amplitude of 2. Tell me, what's this going to look like 1 second later? What's that?
Oh no, I was asking Brianna a question about why was it down below?
Oh, because I'm going like second by second? I don't know. So this is like, this is at 0 seconds, this is 1 second, and then the next one I draw is going to be 2 seconds. I mean, I got to show it somehow. I
I
don't
was just curious.
Yeah, no, I'm glad you're asking. That means you're paying attention. That's good. That makes me really happy. So someone please describe to me, because I'm not going to keep beating this dead horse. Just someone describe to me what's going to happen the next second. What's it going to look like?
Beginning.
What's that?
They look like the beginning, just in opposite spots.
Thank you very much, Gavin. I'm just going to call on Gavin from now on. I hope you guys are okay with that. Gavin makes things run so much faster. I guess that's why he's president. But not like Trump. I mean, a good president.
Gavin, are you president because you make things faster? No.
I don't know.
Okay, you guys okay with that? It's going to look just like the beginning, only now they're going on their merry way, right? This is just like when you have a relationship with a person of the opposite sex. You get together, you reinforce each other, you make the both of you greater than you were as individuals, but then you break up and you're just back to the way you were. Is that okay with you guys? That's reality, man. That's the reality of it. Okay, you guys ready to do it on your own? I didn't hear any yeses or no's, so we're gonna do
A
it
lot of
anyway.
social commentary today. A lot of social commentary today.
Here. Okay, I've got these two pulses moving toward each other. They're 1 centimeter apart. They each have an amplitude of 1 centimeter. I want you to tell me, this is at 0 seconds. I need you to draw what happens at 1 second and what happens at 2 seconds. Please do that now. I will give you like a minute. Remember, they're going 1 centimeter a second, and each one of these, spaces is 1 centimeter. Sure. Thank you. Here. Leilani just gave me some biscotti. Oh, it smells so good. I can't believe you made it. Okay, time's up. What did you guys get at 1 second? What does this look like at 1 second? How many people got flat line? Good for you. Is that okay? You okay? You guys flat line also? Okay, good enough. And someone explain to me why. Explain to me in words. Why is it at 1 second a flat line? How can that happen? Yes, Paul. Thank you. They cancel each other out, right? This guy is occupying this space right here, and this guy is occupying this space, okay? And they cancel each other out. So yeah, you got flat line. Does that mean that's it? Both waves are now dead? They're gone forever?
No.
No way. What do I get the next second? Someone describe for me, please. Go ahead. Noel, tell me in words, though.
The one on your left, or on our left, is going to be down, and then flat, and then up. It's going to be the opposite of what you have at 0 seconds.
Okay. So you're saying that here now it's going to be down?
Yes.
Okay. You made me think that this guy's going to
No.
turn down, but it's not.
You should have let me just keep drawing it in the air.
No, I can't let you do anything. Okay. You guys okay with that? You just go on your merry way. Are you guys ready to do a harder one?
Yeah.
That's what I like to hear. Here it comes. Okay. This pulse is going that way, that pulse is going that way. They're all both going at 1 centimeter per second. I want you to find what happens over the next 2 seconds. And then we'll call it quits. Get the next 2 seconds. Oh shoot, never mind, go ahead, keep working, After 1 second, you should get something that looks like that. And unfortunately, time is ticking away, so I wonder if anyone figured out, what am I going to get on the next second? Yes, Alejandro? Alejandro says a flat line. Does anyone agree with him that the next second it's a flat line? Okay, just Fatima. Please look at it. Can you convince yourself that it's a flat line?
Yeah.
Okay, because it is. Good job, Alejandro and Fatima, yeah. You guys okay with that? That this up guy is going to go there, this down guy is going to go there, they cancel. This up guy goes here, this down guy goes there, they cancel. The next second it's a flat line. And again, does that mean that both waves are gone forever?
No.
Heck no. You can't tell by someone taking a picture of a string whether there's even waves on the string. I could take a picture of that string and it would be flatline, and you'd never know that some seconds later you're going to end up with something that's looking like this, you know, where this wave goes on its merry way and this wave goes on its merry way. Okay? All right, then here's the last thing. I need to teach you a couple of words. First of all, interference. When two waves combine and add their amplitudes, they interfere with each other. And that's actually the physics term for it. So from now on, I'm not going to use words like combine or collide. I'm always going to use the word interfere. When someone is on like a movie and they're talking on a walkie-talkie and they go, I can't hear you, I'm getting too much interference. Well, if he's getting interference, that means there must be some other waves combining with his waves or interfering with his waves to cancel them out or alter them in some way. That's interference. You need two waves to come together for interference. First, constructive interference. You tell me, what's constructive interference? What does that mean?
They add together.
Thank you. Yeah, waves combine to reinforce each other. Waves interfere to reinforce each other. You're going to get bigger amplitude if there's constructive interference. The amplitudes are going to be bigger. And of course, the other one is destructive interference. Tell me, was there an example of destructive interference on that board, on those problems we just did? When was I getting destructive interference? Say again?
The flat line.
Yeah, the flat line. Absolutely. I'm getting destructive interference on those flat lines. Absolutely. Waves cancel. They interfere to cancel each other. Alrighty. Hey, that's it. Thanks a lot, guys. Bye-bye.